In this fast-pacing digital world, the technologies that shape our daily lives rely on complex and interconnected processes, many of which are hidden behind the scenes. The story of modern technology, from the microchips powering our devices to the revolutionary of fields such as AI, blockchain, shows an intricate web of engineering breakthroughs, scientific precision, and innovation. In this reflection, we'll walk through five foundational areas. First is the chip manufacturing, then we will go through Moore's law and semiconductors growth, then photolithography, CPU manufacturing, and emerging fields like AI and IoT. Together, they illustrate how each advancement builds on the next, forming the underlying framework of today's digital world. So the journey starts off when modern electronics begins the precise and controlled process of chip manufacturing, which turns raw silicon into the microchips that power nearly every device we rely on. So this complex journey starts with the raw material extraction, where silica sand is purified to produce high purity silicon ingots, which are then sliced to thin wafers to serve as the base of each chip. So these wafers undergo the doping process, in which elements like phosphorus or boron are added to alter silicon's conductivity. It is then followed by the transistor formation, where the transistors are essential for computing are created. So every step requires a dust-free environment, as even a single particle can compromise the chip's functionality. As the wafer moves along the production line, chip layout and design takes shape through photomasks that outline intricate patterns, creating the pathways for electrical to flow. Addition to these, steps like layering, etching, and metal deposition builds up these pathways, forming a functional circuit wherein, after a rigorous testing and packaging, these chips are ready to drive the devices that define our digital world. So, about this, we see how much each manufacturing step relies on precision and technical knowledge, setting the stage for future innovations that we rely on this robust foundation. The chips we take for granted today are the product of immense technological achievement, representing the base upon which all modern computing is built. The semiconductor industry's rapid evolution would not have been possible without the Moore's law, which has guided innovation for decades, wherein in the 1960s, Gordon Moore observed the number of transistors on a chip doubled approximately every 2 years, wherein a trend that sparked exponential growth in computing power. This principle has led to an industry driven by constant advancement, where companies continuously push the boundaries of what's possible in the chip design and manufacturing. For example, in just a few years, transistor counts skyrocketed from 4 to 60, illustrating the accelerated pace of development. Today, massive machines capable of turning liquid tin into plasma helps create sophisticated circuits that power modern devices. So the concept of Moore's law goes beyond just raw numbers. It has a fundamentally shaped the semiconductor ecosystem, from instruction set architecture that determines chip functions to raise the fabless companies that rely on specialized foundries for production. This collaborative ecosystem has given rise to industry leaders like TSMC, whose advanced foundries allow multiple companies to share resources and achieve economies of scale. Reflecting on Moore's law, we see a testament that to human ingenuity and collaboration. The semiconductor industry's intricate structure shows how innovation is not just a product of scientific discovery, but also the result of collective effort pushing technology forward with each generation. One of the critical processes in semiconductor manufacturing is photolithography. It is a technique that enables creation of minuscule circuits within chip. um, starting with wafer production, wherein this process involves cleaning and coating wafers with a photoresist layer to make them light sensitive. The mask alignment and exposure step then uses UV light to transfer circuit patterns onto the wafer. These patterns are etched into the wafer through a series of chemical treatments, leaving behind intricate layers that form the chip's cut circuitry. Originally, a simple writing the light or writing with light technique um, is what photolithography is. So, photolithography has evolved to allow submicroscopic accuracy, supporting the continuous miniaturization of electronics. So this advancement in photolithography have allowed semiconductor companies to push Moore's law even further, with light sources and optics now enabling resolutions of just nanometers. So this process allows for the placements of billions of transistors on a single chip, increasing computing power while reducing the size. So about photolithography, and its role, it's fascinating to consider that each tiny meticulously created feature on a chip supports the devices we depend on. This technology shows that the future of computing relies on our ability to manipulate materials at the smaller scales, making photolithography an important step in achieving both modern efficiency and innovation in microchip production. So the creation of a CPU, or the brain of modern electronics, requires controlled processes that bring together design, material science, and exacting precision. So CPU manufacturing begins with a detailed design phase, where engineers draft circuit layouts and conduct simulation to ensure optimal performance. So this is followed by silicon wafer creation, where purified silicon is transformed into monocrystal ingots, which are then sliced into wafers. These wafers are then patterned with circuit designs through photolithography and doping processes. So, following the creation of transistors, copper interconnects links of billions of transistors into a cohesive circuit and regulars microscopic monitoring, which detects any potential flaws. Finally, the packaging process, which protects and insulates the chip, ensuring the functionality within the device. So the CPU manufacturing process built on a foundation of meticulous design and state-of-the-art technology. From the extract of placement of each transistor to the bonding of protective layers, the journey of CPU creation reveals a relentless pursuit of precision, allowing billions of operations to occur in a fraction of a second within devices like smartphones, laptops, and supercomputers. While hardware forms the backbone, the future of technology lies in rapidly advancing fields like artificial intelligence, machine learning, Internet of Things, blockchain, and more. So each of these fields bring unique strengths. AI and ML, or artificial intelligence and machine learning, power intelligent systems that can learn, adapt, and make predictions. IoT connects physical devices to create smart environments. And as for the blockchain, it introduces secure, decentralized transactions. Together, these technologies are reshaping sectors from healthcare and finance to transportation and entertainment, pushing the limits of what technology can achieve in our daily lives. So this advancement is clear that they rely on the foundational hardware discussed in these previous sections. So the sophisticated chips, CPUs, and photolithography techniques lay the groundwork of AI algorithms, IoT networks, and secure blockchain transactions. So each of these fields represents the next step in the digital revolution, challenging the traditional ideas of connectivity, security, and interaction. The interplay between hardware and emerging technologies highlights a landscape where innovation continuously builds on itself. pushing the society into an era where the boundary between the physical and digital worlds grow increasingly thin. So, this reflection on chip manufacturing, Moore's law, photolithography, CPU production, and emerging technologies showcases a deeply interconnected technological landscape. So each of these elements, while powerful on its own, builds upon builds upon the others to create a cohesive framework that supports our increasingly digital world. From the precise engineering of microchips to the boundless potential of AI, IoT, and blockchain, it's evident that the future of technology is a tapestry woven from scientific innovation, collaboration, and relentless ambition. So together, they paint a picture of a world where technology doesn't just support us. It reshapes phase, every facet of how we live, work, and connect. So that is all. This is Christian Abusca from DC Pet 3-2. Thank you.